Hey kiddos, time for another video. Today we're going to go through and talk about the composition of matter, and actually matter itself, and different forms that it can take. You should remember from long ago, when you were much tinier, that matter is anything that has mass and takes up space. And we can actually break down matter into two different categories. Substances, and we'll go through and we'll look at those in a little bit, and mixtures, and we'll save that for the second half of this PowerPoint video. So we're going to start off zooming in on substances. And substances basically break down into two further categories, one of them being elements, the other being compounds. Now, at this point, you should have a periodic table with you that basically goes through and lists every single element that is known to man currently. And we're still discovering some, so obviously periodic tables change. But realistically, an element is composed of a pure substance that has only one singular type of atom in that given object. There are 118 known elements, and 92 of them naturally occur, which means anything past 92 is stuff that has to be created in a lab. So we've got all of this down here, and everything over here. None of those elements actually occur naturally in nature. The only thing that ever comprises an element is if it happens to be found on a periodic table. If it is not found on this periodic table, it is not an element. So your examples would be stuff like hydrogen, or carbon, or what do we got here? Calcium, Mr. Banker's favorite element, potassium, oxygen, that's stuff that you breathe, chlorine, the things that make your eyes burn in the pool, bromine, or iodine. Okay? Every single one of those is an element. If it's not on this table, it is not an element, and that should be your first task if you ever have a question on a test or a quiz or on a handout that says, is it an element? Look through the periodic table, because you're not going to find carbon dioxide anywhere on this table. You're not going to find salt anywhere on this table. Those are made up when you take multiple elements and put them together. Anyways, get enough elements in. Basically, we got to figure out how to write them, because we're going to spend the next couple weeks writing them in class. Basically, the symbols are written with the first letter as a capital, and if there is a second letter, that's a big if, it is lowercase. Okay, so example, hydrogen we write as a capital H. Carbon is a capital C. Oxygen is a capital O. Calcium happens to have two letters, so it is a capital C and a lowercase a. And neon, capital N, capital E. We're going to go through and we will have about 30 elements that you have to be able to identify the name and the symbol of, because we will continue to use them frequently in class. But other than that, it's not like you're going to have to memorize random elements throughout the periodic table. When we look at atoms, or when we look at elements, we are going to talk about atoms a lot. And an atom is realistically the smallest unit of an element that still maintains that properties of the element. Okay? So for instance, if I had a chunk of gold in my hand, an atom is going to be the very smallest form of that chunk of gold that will still maintain the same properties of brittleness, or malleability, or shininess, or melting point and boiling point, etc. Once we break down further than an atom, and there are things that make up atoms, and we'll talk about those in Unit 2, once we get further than that, they do not anymore have the same properties. So an atom is going to be the smallest part that maintains the same properties of the element itself. All atoms of an element are going to be alike, so every gold atom is going to be like every other gold atom in a chemical sense. And so Au, we talk about as gold, every atom of Au is going to be the same. Yes, it is a very large generality. We are going to look at in the coming weeks how you can have slight changes here and there, but they are chemically, and they will have the same properties being identical to each other. Okay? Compounds, on the other hand, are going to be when we have two or more elements bonded together in a fixed position, and this is where your water comes into play. Every single time we have a molecule of water, it is going to come out with two hydrogens and 1 oxygen. Okay, every single time. So that guy's right here, water. Other things that you may know would be carbon dioxide, the stuff you exhale. NaCl is going to be table salt. C6H12O6 is going to be sugar. The C8H10N4O2, if I remember correctly, is caffeine. And our final one, C2H5OH, is going to be alcohol. Every single time you go through and create one of these objects, carbon dioxide, salt, it will come out as the exact same proportion. So every time I have table salt, it's always going to be 1 sodium and 1 chlorine. Every time I have carbon dioxide, it's always going to be 1 carbon and 2 oxygens. So that's something to keep in mind there. If you see 2 different elements written together with no spaces, it is a compound. Notice how there's never a spacing between any of the letters. You cannot separate a compound by physical means. If we're going to separate a compound, what we need to do is we need to chemically break the bonds that are between those atoms. So we need to chemically break that and chemically break that. I cannot just physically chop it apart. You will have to put it through a chemical process, and we'll talk about that in a little bit. Compounds happen to have a different appearance and different properties than the individual elements that make them up. For example, NaCl is table salt. Okay, table salt is made up of sodium, which is a metal that reacts with water and kind of ignites when it reacts with water, and chlorine, which is a poisonous gas. So when you're eating salt, you happen to be eating a metal that blows up when it touches water, and a gas that's very, very, very poisonous. But when they combine together, they form table salt, which is totally safe in moderation. Obviously, too much of it, not good for your health, but in moderation, good and delicious. It makes my French fries taste better. Okay, so the compounds are always going to end up having slightly different, not slightly different, different properties than the 2 elements that make them up, or 3 elements that make them up. In terms of a molecule is basically going to be a 2 or more of the same atom bonded together in a fixed position. Okay, these atoms do not need to be different atoms. Okay, so hydrogen bonding to another hydrogen is a molecule. Oxygen bonding to oxygen is another molecule, but we could also have carbon bonding to 2 oxygens as a molecule, and hydrogen bonding, or 2 hydrogens bonding to an oxygen as a molecule. Basically what a molecule is, it's going to be one of the smallest versions of, in this case, a compound, so the smallest form of a compound that still maintains those properties, or when you get 2 atoms of the same element bonding together, and it's just 2 individual atoms. Okay, so molecules are the smallest form of a compound. They can exist and still have the same properties, but it can also include, again, multiple versions of the same element bonding together. Zooming out, that was all of our substances stuff, and we'll have a table that kind of walks us through it in a second. But let's hit mixtures now. Okay, this is our second form of matter, which again, anything that has mass and takes up space. So mixtures basically go through and contain more than one type of matter that are not chemically bonded together. And that means we can separate them physically. Now, whether we're talking about, hey, I can pick them out with my fingers, or whether I have to go through boiling and freezing and distillation processes, I can go through and I can separate any type of mixture physically. And we've got 2 types. We've got homogeneous and we've got heterogeneous. Okay. Heterogeneous mixtures, the matter is not made up of the same proportions. Basically, you can pick out the different parts of the mixture very, very, very easily. They are very distinguishable. Okay. Examples I like to use are cereal, trail mix, cookie dough ice cream, which is amazing, a Kit Kat bar, a Snicker bar, anything where you can see the different parts of it. You're going to end up having a heterogeneous mixture, and you could physically pick out different parts. Okay, so again, those can be physically separated. The curveball that you guys are going to see most of the time, or most of you guys are going to think, is a homogeneous mixture, because they are perfectly evenly blended. Okay, so for instance, soda. the high fructose corn syrup, the sugar, the dyes, the water, everything that's the carbonation, everything that's inside the soda is perfectly evenly blended so that the first sip is going to taste exactly like the last sip. Air, the air that you breathe, I believe 78% nitrogen, 21% oxygen, 1%, I can't remember that one off the top of my head, the rest of it's just trace elements. But it's evenly spread out. It's not like in this corner of the room I get more oxygen, in the other corner of the room, oh my gosh, there's no oxygen. It is evenly spread out everywhere. And chocolate ice cream, salt water, Kool-Aid, all of these are going to be perfectly evenly blended, making them homogeneous mixtures. And we call that a solution. In Unit 5, we're going to come back to this idea when we talk about acids and bases. But a solution is basically, or essentially, a perfectly evenly blended mixture. Okay? Now the problem with this, most of you children are going to get caught up thinking because I can't see the different parts, I need to chemically separate it. That is not true. Being a mixture, it can be physically separated. Now the way that we would physically separate this, because you can't see them, is by boiling at different temperatures or by freezing at different temperatures, and you will try to work out individual portions one at a time by boiling and freezing, by changes in states of matter, or by filtering, or however you go through and do it. But you can physically separate each of these different mixtures. Okay? And so homogeneous versus heterogeneous, again, this is just a quick little example. Heterogeneous mixture here with granite, even though when you're looking at a granite countertop, for instance, you can see the different portions that are making up that rock. And the purple's a little hard, but you can see, your small little white area, your black area here, your yellow, your green. These are different original parts that were put together to form that granite rock. Human blood is actually going to be a heterogeneous mixture, because when you look down at it, there's going to be your red blood cells, but you're going to have white blood cells, you're going to have platelets intermixed in with all that. However, when we take a copper sulfate, or a copper 2 sulfate in water, it is going to be homogeneous because it is a solution. When you zoom down into its finest state, you are not seeing a separation between copper and sulfate. It is all perfectly evenly mixed in. So that's kind of where we're looking at with the homogeneous and heterogeneous examples. And again, if you want to double check your book, you're going to have some good examples in there as well. So overviewing of today's PowerPoint or video, we start off with matter, which is anything that has mass and takes up space. And we have two parts of it. It can get broken down into mixtures, which we know can be physically separated. And these substances need to be chemically separated. And for those of you that are following along and actually picking up on stuff, your mixture is going to break down into homogeneous mixtures and heterogeneous mixtures, where these are evenly mixed, and these are uneven. You can pick out different portions of it with your eyes. The substances, however, are broken down into two parts. You've got your elements, which are going to be composed of only one type of atom, and then you've got your compounds, which are composed of more than one type of atom bonded together in a fixed position. So this is one atom type only, and this is 2+ atoms bonded together. But your big key to that is the fixed proportion. I'm not going to write out proportion, but this is your idea, the fact that it's going to be a fixed proportion. Every time we exhale carbon dioxide, it's 1 carbon, 2 oxygens. And we'll talk about how that works later in the semester. Anyhow, that was our overview of matter. We'll work through some examples in class a little more, but that should give you a good start.